Hi, I'm Fabian. I'm a PhD student at MIT, working with another student, Oscar, and my advisor, Sam Madden, on research projects involving analyzing large-scale image and video datasets. In this talk, I'm going to demonstrate Vaas, a system we built for performing video analytics at scale. Vaas accelerates the development and execution of a wide range of tasks. And just to introduce some examples of the kinds of tasks we're talking about, in traffic camera footage, an analyst may want to find segments of video where cars run red lights, or perhaps measure the per-direction traffic volumes. In dashcam video, we could use Vaas to measure, for example, the average delay between a light turning green and a car starting to accelerate. Or in wildlife video, we could find various interesting events like when a bear catches a salmon in the video. To enable these tasks, Vaas addresses two key challenges in video analytics. First, developing query pipelines for complex multi-stage analytics tasks, and second, efficiently executing those pipelines, which often involve expensive deep neural networks on large video datasets. So I'm going to jump straight into a demo to show an example of using Vaas for video analytics, and specifically we're going to find segments of video where a car runs a red light in some traffic camera footage, so the first example application that I discussed. So this is Vaas. I've already imported some traffic camera footage in this dataset called Tokyo Traffic Camera. And again, our goal for today will be to find segments of video where a car runs a red light. I'm going to go to queries and first add a new query for this task. Let's call it find car red light. Before adding any operations, let's just get a sense for what the video looks like. So in predicate and rendering, we can specify essentially the select and where clauses of our query. By adding this input 0, I'm saying this query should act as an identity operation and just render its input directly. Now we can go over to the exploration tool and run our query. Here, Vaas will run the query over 30-second segments of video uniformly sampled from the dataset. The dataset could be one video or multiple videos. Vaas will work either way, and it samples 4 segments at a time. And the sampling is configurable. We can change the length of the video we want to sample, or sample sequentially from some starting timestamp instead of randomly. This is what the video looks like. There's a traffic light visible here, so we can see whether it's red. And we're going to focus on cars that go from the bottom right of the video to the top left while that light is red. To do so, we're going to first find cars that go from bottom right to top left, and then we'll classify the traffic light color, whether it's green or red, and finally we'll join those two together. Alright, so let's begin the first task, finding cars that go from bottom right to top left. Let's apply a YOLO v3 object detector. YOLO v3 is a model that will input frames from our video and output bounding boxes around various detected objects. We also need to add the new operation to our select clause. This tells Vaas to overlay the YOLO v3 detections on top of input 0, the input video. Now when we run this query, we see a bunch of detections computed by YOLO v3. But here it's including detections of pedestrians and a bunch of other objects, so let's get rid of that. To fix it, and just extract the car detections, we can go back to our query, and Vaas has a detection filter operation that we can choose and configure to keep only the cars. I'll also add a tracker to associate detections of the same car. And finally, let's also add a track filter that selects cars that go from bottom right to top left. To do that, Vaas lets us simply draw some polygons, specifying the regions that we're interested in. So I'll draw the first in the bottom right and the second in the top left. So Vaas is going to select the cars that go through those polygons in order. Now we'll add the select clause, and we'll adjust the select clause and run the query again. And you can see we are getting those cars that go straight through the junction from bottom right to top left. The boxes indicate the cars that pass the polygons in our track filter. So at this point, we've completed our first subtask. And now let's try to classify the color of the traffic light. We want to do binary classification, output 0 if the light is green or yellow, and 1 if it's red, which is what we want. To make this part simpler, let's first crop the video to just capture that traffic light. So using Vaas, we can just draw a box around the crop that we want to extract. Now, to classify the light color in that crop, I'm going to apply a simple image classification model. We'll need to annotate a bunch of crops to get some training data for that model. So I'll create a new annotation set. So I'm pressing 0 when I see a green or yellow light, and 1 when I see a red light. A couple hundred examples is going to be enough for the classifier, and that actually only takes 2 or 3 minutes to label, so it's really fast. We can go back to our query, add a new classifier operation, and train the classifier on the labels that we just added. Since the crops are so small, training is going to be really fast. To verify our classifier's performance, let's render the classes that it outputs. I'll update the select clause and then run the query again. So it seems to be working now. When the light is red, the class at the top left is 1, and when the light is green, it's 0. Finally, we can join the filtered tracks with the light color to find just the tracks that go straight through the junction on a red light. I'll add a custom Python operation for this that will input both the tracks and the traffic light color classes. This Python function loops through all of the tracks and only keeps the ones where both the first and last detection in the track coincide with a red light. Vaas makes it really easy to write short Python functions like this and integrate them into your query, both through its Python library and by allowing users to quickly iterate on their script and experiment with different modifications. We'll also set the output of this operation as the query's predicate. This is essentially our query's where clause. If we don't find any tracks that ran the red light in some segment of video that Vaas is currently testing, then we'll skip that segment and Vaas will test another and another and another until it finds something that satisfies this predicate. Okay, let's run the query one final time. It takes a bit longer now because we added the predicate, so it has to do more work for each output. It's processing a lot of segments where there was no car running red light incident and skipping those segments. But indeed, we get a video out, and we can see that there's a car that enters the junction just after the light turns red. Alright, so that's it for the demo. To summarize, Vaas addresses two key challenges in video analytics. To accelerate the development of query pipelines, Vaas provides a query composition tool that enables easily composing diverse operations to achieve complex tasks, and a data exploration tool that enables quickly visualizing the outputs of various operations in a query on segments of video sampled from a large dataset. To efficiently execute queries both in an interactive setting or in batch settings where users want to extract information from entire datasets, Vaas effectively combines several optimizations proposed in recent work that I didn't get a chance to cover. Finally, at vaas.csale.mit.edu, we have examples of applying Vaas on other tasks as well as the source code.